Hi, everybody. Welcome back to Dave's Math channel. I haven't been making too many videos on this channel lately, and I apologize for that. I guess I got kind of sidetracked for the last month or so, and I especially haven't made any videos on my series on algebraic number theory. And I apologize for that as well. Part of the reason for that, like I said, I got sidetracked with a lot of other stuff, but also it turned out that ultimately I want to prove that the ring of Gaussian integers is a unique factorization domain. I thought I could pretty easily prove that given the information I already gave you, but it turns out that's not the case. I was kind of struggling with a proof, and then I kind of got frustrated. But I will prove it. But the way I'm going to prove it's going to turn out to be a little more complicated than I thought. I'm going to use the standard proof, which I'll get to later. I'll get to at the end of this video. But now I'm going to change tracks a little bit. Instead of talking about Gaussian integers, we will get back to Gaussian integers and Gaussian primes. But before I do that, I want to talk about rings and ideals. And these are very basic properties in algebraic number theory. So I think it is really worthwhile that I talk about them. So anyway, let's begin. So first, I'm going to start with a bunch of definitions, and some of these are rehashes of definitions I've already given you. So now I'm going to redefine a ring. I think I already defined rings before, but I'm going to do it here anyway. So this is a little bit more of a detailed definition of a ring. So a ring is a set with two binary operators, which we call addition and multiplication. So here I'm using plus for addition and times for multiplication, and it satisfies these six axioms. So first is closed. It's closed with respect to both addition and multiplication. That means that if you have any two elements, little a and little b of capital R, then both their sum, a plus b, and their product, a times b, which we can also write as ab, are also elements of R. And then the second property is associativity. And once again, both addition and multiplication are associative, which means that it doesn't matter the order in which you add three elements or multiply three elements. You can group them two different ways, doesn't matter how you group them. And then commutativity with respect to addition. It turns out that it's not necessary for a ring to be commutative with respect to multiplication. There are times when we might want to study rings that are not commutative with respect to multiplication, but they're always commutative with respect to addition. So we do have the commutative property with respect to addition, namely if A and B are two elements of the ring R, we have A plus B equals B plus A. Then we have the additive identity element. So there's an element of our ring which we call 0. That's the additive identity. It just means that for every element A of R, we have A plus 0 equals 0 plus A equals A. And then, and we also don't have to have a multiplicative identity necessarily. If we did, we'd call it 1. But we don't have to have that. There are examples of rings that don't have multiplicative identities. And I think we will see some of those later. And then they have to have an additive inverse. So if A is on the element of the ring R, there has to be another element which we call the negative of A or minus A, such A plus minus A, which is also going to minus A plus A is equal to 0. And for shorthand, we write A plus minus B as A minus B. So you can think of subtraction as adding an additive inverse. And then finally, we have the distributive laws, namely A times B plus C is equal to AB plus AC, and also A plus B. The quantity A plus B times C is AC plus BC. So if it satisfies all six of these axioms, then it's a ring. And I think you guys are all familiar with the fact that the integers is a ring. Just think of the integers as sort of a generic example of a ring. And we already went through that next time. So now I have a few more definitions. Like I said, not every ring has to be commutative, but if it's commutative with respect to multiplication, we call it a commutative ring. So that satisfies the seventh axiom, namely commutativity with respect to multiplication. So if A and B are any two elements of your ring R, then AB equals BA. And then we have another special type of ring, which we call a ring with identity, or a ring with one sometimes. That's just a ring that has a special element, multiplicative identity element, which we call 1, such that for every element A of your ring, A times 1 equals 1 times A equals A. So, and then, since we study commutative rings with identity so often in number theory and algebraic number theory, we usually just say ring instead of commutative ring with identity, because almost every ring we study is going to be a commutative ring with identity. So from now on, whenever I say ring, unless I say otherwise, we can always assume that we're talking about commutative rings with identity. And and then I think you guys also know I gave you this definition already of a field. A field is a special type of ring. We usually use the letter F for a field, and it satisfies a ninth axiom, namely multiplicative inverse. And what that says is that for any non-zero, it's very critical to non-zero. For every non-zero element of your field F, so if you have non-zero element A, there exists another element of your field which we call A inverse. It's the reciprocal or multiplicative inverse, if you like, of A, such that A times A inverse is A inverse times A is 1. So that's a field. Anyway, so those are some pretty basic definitions, which I already went over last time. I'm just going over them again because they're very important. And then here's another definition. This is something we haven't seen yet. And this is a very important concept. This is what's called an ideal. So every ring, and again, we're assuming our ring is a commutative ring with respect to identity. You can define ideals for more general rings, but we don't. Those are more complicated. So let's assume R is a commutative ring with identity, and then we can define this thing, this subset of R, which we call an ideal, and we usually use the letter I to represent an ideal. So an ideal I of R is a subset of R, and it inherits the addition and multiplication from R that satisfies two properties. So the first property says that for every two elements A and B and I, the quantity A minus B is also an I. That turns out to be just a fancy way of saying that I is a subring of them. And I doesn't have to be have the identity. It does have to be commutative with respect to multiplication, but it doesn't have to have the multiplicative identity. As a matter of fact, most of the time it doesn't. But it is a ring, just not a ring with identity. It is a commutative ring. And then the other property of ideals, and this is the more interesting property, I think. So you take any element A of your ideal I, and any element little r of the ring, capital R. It turns out the product A times R is a new element of I. So you're kind of stuck in I. And I've heard a very useful analogy. You can think of ideals kind of like a black hole. Because once you go in, you can't come out again. I mean, if you start with any element A of your ideal, then you multiply that by any element of the ring. It doesn't even have to be in the ideal, but just any element of the ring. You're stuck in the ideal. The product's still in the ideal. There's no way you can get out. There's nothing in R you can multiply an element of the ideal by to get outside of the ideal. Once you're in the ideal, you're stuck in the ideal. I think that's a nice way to think about ideals. They're sort of like black holes. Anyway, so now I'm just going to give you some examples. And these are all very similar examples, it turns out, but they're important examples. So let's let R be our familiar ring, namely the ring of the integers, ordinary integers, Z. And it has the ordinary addition and multiplication. And let's let I be the subring 2Z. So it's the subring of even integers. Just half of all the integers, the even ones. And I'm claiming that the even integers is an ideal of the ring of the integers. And that's actually pretty easy to see. Because we just have to check that these two properties hold. So the first property, let's let A and B be any two even integers. And that means that A has to be 2m and b has to be 2n for some integers m and n. Well, now let's consider the difference, a minus b. Well, that's 2m minus 2n, which we can also write as 2 times m minus n. And of course, that's going to be even because m minus n is an arbitrary integer. We're multiplying by 2, so we're left with an even number. So that means that we are still in the ideal of even integers. And the second property we have to check, if we take any even integer and multiply by any other integer, it doesn't even have to be even, we're left with an even integer. I mean, that's pretty obvious, right? So let a be 2m again, and let r be an arbitrary integer. Well, then you take the product, you get 2mr. And since m and r are integers, that means 2mr is an even integer. So yeah, once you start with an even integer, it doesn't matter what you multiply by, you're always going to get an even integer afterwards. That's pretty obvious. So the even integers are an ideal of the ring of integers, ordinary integers. And I think I put these out of order, but yeah, I probably should put this slide earlier. So I already mentioned commutative rings with identity. So here's how you can think about these things. I mean, here's a useful Venn diagram. So we got groups on the outside, and groups actually, I don't know if I quite like how they put groups in here because I don't really think of rings as a subset of groups. I mean, rings are a special type of group. They're groups with respect to addition. They're abelian groups with respect to addition. I guess in that sense, they are a subset of the set of groups because they're abelian groups with respect to addition. Abelian, not all groups are abelian, as you probably know. There are groups that the elements, the group multiplication doesn't necessarily, it's not necessarily commutative. There's a lot of examples of groups like that. You probably all know, like S3. I'm not going to go into that because I'm not going to talk about group theory here. But abelian groups are a special type of group, and it turns out every ring, if you just look at addition, it's an abelian group with respect to addition. But it also has another operator which we call multiplication. So not only is it a subset of the set of groups, it also has an additional structure. But now we can talk about special types of rings. We can talk about commutative rings, and not every, like I said earlier, not every ring is commutative. So that's a subset of the set of rings. And also we have rings with identity. And like I said, also not every ring has the identity element in it. So this is an accurate Venn diagram here. The set of commutative rings is a subset of a set of rings, and so is a set of rings with identity, but then they intersect. We also have commutative rings with identity. That's what I'm calling rings now. So that when I say the word ring, you really should be thinking of this kind of sideways eye in the middle. It's the intersection of these two dark blue subsets of the set of rings. And then inside that, we have the set of fields. So field is an even smaller set. So it turns out fields are always commutative rings with identity. I mean, fields always have to have the multiplicative identity element. And they also have to be commutative. I mean, there are things called skew fields. You can define fields that aren't commutative with respect to multiplication. Those are a little weird. I mean, they can be useful. Quaternions, for instance, or yeah, quaternions is an example of what's called a skew field. It's not commutative with respect to multiplication, but those are a little bit weird. Most fields people study in math are commutative with respect to multiplication, so they are a special type of commutative ring with identity. But not only that, they have additional structure as well. Like I said earlier, every non-zero element of a field has a multiplicative inverse. That's not necessarily true of commutative rings with identity in general. So anyway, that's a nice Venn diagram to kind of see what's going on. But anyway, let me just continue with my examples. So, and then these two examples are basically the same examples my previous one, just a little more general. So now, instead of considering just even integers, let's consider multiples of some non-zero integer k. So let k be a positive integer. It's easier to think of positive ones. And, let z r be the ring of ordinary integers z with, ordinary addition and multiplication. And now let's consider this set kz. just multiples of k, and I'm claiming that that set is an ideal of the ring of integers. And it's the same argument, basically, as the last one. I mean, we have to check the two properties. So first we have to check that if A and B are elements of our ideal, in other words, A is equal to K times M, and B is equal to K times N for some integers M and N, then A minus B is going to be Km minus Kn, which is K times M minus N, which is indeed a multiple of K. So that shows that it satisfies the first property. And to get the second property, you just take an arbitrary element of your ideal A is Km, and multiply by any integer, N, and then you get Kmn, and obviously that's a multiple of K. So once you start with a multiple of K, you multiply by any integer, you're left with another multiple of K. So that means that the multiples of K do indeed form an ideal of the ring of ordinary integers. And third example, and this is the most general, this is kind of the biggest generalization I can make of examples 1 and 2. Now I'm no longer considering the ring of ordinary integers. Now I'm letting R be an arbitrary commutative ring with identity. And again, K is an arbitrary element of R, and it doesn't even have to be non-zero. It could be zero as well. So anyway, now I'm claiming that the ring, which I'm calling K capital R, which is really just the subset of R consisting of all multiples of K in R. In other words, all elements that form little k times little r, where little r is an arbitrary element of big R, that set with, that inherits the same addition of multiplication from R, that set is an ideal. And it's basically the same. The proof is the same proof. We really don't have to change anything here. So now I'm going to let S and T be arbitrary elements of capital R. And now, I mean, if A and B are arbitrary elements of the set KR, that means that A is equal to KS and B is equal to KT for some elements S and T of our ring R. And then we do the same thing. We just A minus B is KS minus KT, which is K times S minus T. And obviously that's a multiple of K, so that is an element of KR. So that proves the first property. And the second property, we start with an element A equals Ks of KR, K times capital R, and we multiply that by an arbitrary element little r of capital R, and we get Ks times R, which we can also write as K times SR because of the associative property of multiplication, and that is indeed an element of K times capital R. It's an ideal element. That proves that this set is an ideal. So anyway, and like I said, K could be 0. Anyway, and now I'm going to give one last definition here, namely, well, I guess two, but the first definition I'm going to give, this is a special type of ideal known as a principal ideal. And it turns out all the ideals I've shown so far are principal ideals. There are other ideals that aren't principal. And we'll look at some later in this course, but not today. But a principal ideal is just we can kind of, the last example was the most general example of a principal ideal. A principal ideal is just, we start with a commutative ring with identity, which we call capital R, and then we take an arbitrary element, little k, of capital R, it could be 0, and then we define, we say that a principal ideal is an ideal of the form little k times capital R for some element little k of capital R. That's how we define a principal ideal. So for instance, if R is the ring of integers, ordinary integers, then all the principal ideals are just multiples of some integer k. Those are all the principal ideals of the ring of ordinary integers, just multiples of some fixed integer. And then, without loss of generality, we can assume it's a non-negative integer because if k was, say, minus 2, it's pretty easy to see that that's the same ideal as if k is 2. Anyway, so that's what a principal ideal is, and then like I said, k could be zero, and in that case you get what's called a zero ideal. That's not a very interesting ideal. I mean, it's an important ideal, but it's an ideal that has just one element. As a set, it's just the singleton zero. So it's really just a set with the single element zero. And, when you multiply anything by zero, you always get back zero. So it's pretty obvious it's an ideal by this definition. Also, zero minus zero is zero. So, it's kind of a trivial example of an ideal, but it's called the zero ideal. And now there's one last definition I'm going to give here. Principal ideal domain, abbreviated as a PID. And a principal ideal domain is a special type of ring R, such that every ideal of R is a principal ideal. Not every ring, not even every commutative ring with identity has this property. We will look at some rings that are not principal ideal domains. And the reason we're calling it a principal ideal domain, it turns out that principal ideal domains are always integral domains. And I defined integral domains in a previous lesson. I didn't define them in this one. Maybe I should have. But basically, an integral domain is just a ring with no zero divisors. That means that if A and B are any two elements of your ring R, and then if A, B equals zero, if the product is zero, that means that either A is zero or B is zero. And that's obviously true for the ordinary integers. It's also true for the Gaussian integers. It's going to be true for most rings we look at. Most rings we study in this course are going to be integral domains, but not every ring is an integral domain. There are rings with zero divisors. As a matter of fact, it's pretty easy to find some, like the ring of integers modulo n, where n is any positive integer, like the ring of integers modulo 6, for instance. 2 times 3 is 0 modulo 6. So 2 and 3 are zero divisors in that ring. So there are interesting rings that are not integral domains, but most rings we study in algebraic number theory do turn out to be integral domains. And we also studied Euclidean domains. Those are just integral domains for which you can apply the Euclidean algorithm. I think I talked about that a few lessons ago. Turns out we proved that the ordinary integer is a Euclidean domain. Not only that, I think we also proved that the ring of Gaussian integers is a Euclidean domain. So Euclidean domains are very important. And another reason Euclidean domains are really important, I'm not going to prove that today, but it turns out that every Euclidean domain is also a principal ideal domain. And since we already know that, for instance, the ordinary integers and the Gaussian integers, we both know that both of those are Euclidean domains. That already proves that both of those rings are also principal ideal domains. That means that every ideal of the ordinary integers is a principal ideal. We haven't proved this yet because we still have to prove that every Euclidean domain is a principal ideal domain. I'll do that next. And that'll also prove that the ring of Gaussian integers is a principal ideal domain. Every ideal of the Gaussian integers is also a principal ideal, it turns out. And kind of the icing on the cake on all this, it turns out that there's another implication. It turns out that every principal ideal domain is also a unique factorization domain. I think in the previous lecture, which I did like a month ago, I proved that the ordinary integer z is a unique factorization domain, which is basically the fundamental theorem of arithmetic. It says that every non-zero integer has a unique factorization as a product of primes, of the ordering of the prime factors. And it was a pretty difficult proof. And it turns out that the Gaussian integers is also a unique factorization domain. I was going to try to prove that a different way. I thought there was going to be a nice simple proof of that using the fact that the ordinary integers is a UFD, but it turns out I don't know if there is. I don't think there is a simple proof. That's why I kind of got stuck. But if we can prove that every Euclidean domain is a principal ideal domain, and in turn every principal ideal domain is a unique factorization domain, then we'll be in business because we already know that the Gaussian integers is a Euclidean domain. So it'll follow the Gaussian integers a principal ideal domain, and further that it's a unique factorization domain. And then we'll be able to do a lot of nice stuff with Gaussian primes. In particular, we'll be able to classify all integers that you can write as the sum of two squares, and we'll show how to do that and how to get every such representation, which is a really nice result and has a lot of important applications in terms of, for instance, classifying all um, um, Pythagorean triples or primitive Pythagorean triples. So there's a lot of stuff we can do. We'll get back to ordinary numbers pretty soon. And remember, I was talking about lifting your domain. I mean, the reason we're talking about all these abstract concepts right now is because we're sort of lifting above the ordinary integers. We're studying more abstract sets. In this case, rings and ideals and domains and all this, but we're going to come back down to earth at some point, and we're going to use some facts about Gaussian integers and Gaussian primes to prove some interesting facts about ordinary integers. That's where we're going with this. So anyway, once again, I apologize for the long delay in my videos, but I guess we're back on track now. So thank you for watching. Long live math, and I'll see you guys next time. Bye.